Okay, welcome all back. We are ready to introduce our final speaker for today, to be followed a little later by our panel session, so don't forget to submit your questions. It's my honor to introduce Mr. Matt Mickelson, or Mickelson, excuse me. He's the principal in MITRE's Naval Program Division. He has spent 20 years integrating emerging technologies, including cyber, AI, and autonomy, to improve some of the world's largest organizations. He has given talks in academia and industry. He has been a keynote at an IEEE ICT-AI conference and an invited speaker for the National Cybersecurity Alliance at NASDAQ. He actively coordinates advanced research programs in cybersecurity at the Office of Naval Research. Thanks very much for being with us today, Matt, and talking to us about causality and a strange title, Curious Blend of AI and Determinism. Thanks very much, Matt.
All right, well, thank you, Joe. And thanks to the panel and the rest of the speakers, and thanks to the committee and the board for inviting me to come and talk. I'm going to go ahead and kick it off. A lot of these things, I'm going to harken back to a number of topics that were discussed by some of the previous speakers, and I think that's fantastic. So I'm going to start things off by just letting you know what's coming at the end. I am indeed going to talk about causality modeling and how we can use it to bound and improve some of the AI and machine learning models, and how this enables you to use AI and machine learning more effectively and in more use cases than you might ordinarily think. Before we do that, though, I'm going to take a page out of a number of other folks, and we're gonna look backwards before we look forward. Data science is not new. Math is not new. It's been going on for a long time. If we go all the way back to ancient times, we see that there was a very complex system of risk modeling. All the way back, 4,000 years ago, ancient Babylon, ancient Greece, ancient Rome had both the underwriting of ships and voyages, but also maritime insurance of the cargo and the personnel and the equipment. And this is obviously not possible without at least rudimentary understanding of the probabilities involved in the mathematics to make it happen. Jumping forward a bit, we'll go into the 17th century and the development of calculus. We've got Newton and Leibniz over there staring us from the corner, originating the concept of the limit, allowing us to think about.
Pardon me, Matt, pardon me. Are you showing slides?
I am. I should be. Are you not seeing them?
No, we're not seeing them. Sorry.
Oh, okay. 1 second. There. Are you seeing them now?
Yeah. Yes.
Okay. Excellent. So here we are in the 17th century. Let me get this slideshow back. All right. So there, now we have Newton and Leibniz looking at us. The 17th century saw the advent of calculus, which allowed us to conceptualize the notion of a limit as numbers tend towards infinity, towards zero. It gives us the ability to now talk very formally about infinitesimals and the science of changes, instantaneous changes as opposed to step changes. It allowed us to begin discussing infinite series, infinite sums, and continuous processes as opposed to discrete ones. In the 19th and the 20th century, we saw the evolution. A number of previous speakers that actually talked about Turing and Enigma, and you actually see a picture of the bomb in here from Bletchley Park. The advent of mechanical calculators that allowed us to do faster calculation with less error, and even rudimentary and modern electronic computers that digitized the process that made it even more repeatable and scalable to the sizes of the data sets that we see today. So today we have the advent of artificial intelligence, machine learning, neural networks, and I'm not going to drive too fine a point or too fine of a distinction between these and the rest of the talk. I'm gonna use them sort of synonymously throughout, under the guise of largely probabilistic data models. So before we really start talking about how things have changed and how they've gone forward, a few words about change from our friend Douglas Adams, the author of, among other things, The Hitchhiker's Guide to the Galaxy. So everything that's in the world when you're born is just normal. Most folks don't understand how you possibly could live without it, how you could exist and go on without such things. Between age 0 and 30, things that get invented during that time are exciting, they're creative, you can make a career out of it, you can research it, it's fun and it's new. And then everything that gets invented after you're 30 is against the natural order of things and the beginning of the end of civilization as we know it. So what's really going on? Are things actually changing, or are they really staying the same? And I would argue no. We are seeing some changes. So AI is very legitimately affecting how we're modeling things. It's allowing us to model and do calculations on previously impractical systems, things like vision, audio, video, behavior, natural language, written language, political systems, social systems, market systems. You'll notice a theme here. Most of these things tend to be non-deterministic systems, and they tend to be very complex and not really geared for traditional mathematic deterministical models. AI is also affecting how we're abusing those models too. The reduced cost of being able to do these large complex calculations has really amped up the ability to both attack and defend those models. It has enabled folks to automate what was previously only attributable to human activity, and it's created new threats as a result, or threats that were previously only practical by large, enormously funded nation states or organizations or groups of folks. It's allowed exquisitely fine targeting of folks, as you've seen take place in the online advertising industry. And that's allowed us to scale to those non-deterministic systems that we saw on the previous slide. It's also introduced what I refer to as Schrodinger's ghost to data analysis and data science in particular. And when I refer to Schrodinger's ghost, it's really the superposition of equal and opposite states. AI and AI models are now confounding facts with mistakes, right? It is very difficult after a model has been trained and put into production to really tell the difference between the result, whether the result is true or whether the result is a potential mistake, unless you have some sort of outside third-party model or observer to let you know when we're having mistakes. And we'll come back to that in a later slide. It's also creating a superposition of the results and the processes, right? The age-old end justifies the means. No, it doesn't. It's not always okay just to get the right result. The process in many ways is just as important as how we got the result. And we'll come back to that one as well later on down the talk. So here's a few examples of what I was talking about in terms of being able to tell when AI makes mistakes or not. The picture in the upper left-hand corner was an AI and a model in an effort that shall remain nameless to protect the guilty. But what it was doing is it was attempting to predict the follow-on future values of time series data. So you could think of this as trying to predict the stock market, for example. And what the AI model ended up optimizing for was it discovered that it could actually minimize the distance between its predicted value over time and the actual value over time by simply slipping 1 unit on the x-axis and giving you yesterday's value. So if, for example, this was stock market data, it would simply make tomorrow's prediction based on today's average market value. And if you're willing to bet large sums of money in the stock market on yesterday's closing value, you'll know exactly how much of a mistake that would be. The second one in the middle is an example drawn from computer vision. We've probably all seen variations on this where, you know, the machine learning algorithm picks up on nuances and fine details in the picture and sees things that aren't there. Obviously, this is not a car in the middle of the lake. And obviously, this confounds the problem when we start actually introducing things like adversarial machine learning and all of the adversarial cyber that is happening for trying to trick these models on purpose. So what do we do? How do we adapt to this new thing called AI and machine learning that's happening in our data science world? Well, there's a few things going on. In my day-to-day role with the Office of Naval Research, I sit in the advanced research program, largely in cyber. And so I've seen a lot of things happening in the data science world as they apply to cyber. And here are a couple of things that are happening. The first one is a return to what I'll call the fundamentals, right? You'll see why I call them fundamentals in a minute, because it's going to take us back to the mid-1700s. But it's really getting at the notion of identifying the real causal agents in a system. Said we were going to go back to the mid-1700s, and here we are with Mr. David Hume. We may define a cause to be an object followed by another, where if the first object had not been, the second never had existed. This is basically the first introduction of what we'll call the counterfactual test. And it's basically the premise of how we get to identifying cause, not just correlation in a model or in a data set going forward. However, so let me give you an example first. An observation leads to an action query, which demands a counterfactual as a result. So an example of an observation might be that the system failed. The action query is, well, I suppose maybe did the system fail because there was a component X that was faulty. And then the counterfactual that's associated with that query would be, well, if X wasn't faulty, what would have happened? Would the system not have failed? And then run it through a model and see what would happen. The number of problems with the counterfactual test, though. Once you start applying this, you start to see a number of things go wrong and a bunch of gotchas. So the first one is the obvious dependence on the model, right? The output of your counterfactual test is only as good as the model that you have to actually run it. So the counterfactual can potentially lead you astray off the end of the cliff here in the cartoon if your model is not up to snuff. The next problem you might have is that your model might be good, but it might just be incomplete, right? What if you don't measure enough variables? What if you're not collecting all of the data that you necessarily need? It could be accurate, but if it's not complete or it's biased, the counterfactuals may also lead you astray if you don't have all the necessary variables to come to the proper conclusions. So the questions that you need to be asking yourself in this situation are, if you didn't collect your own data set, who collected it, and what sort of validation and what sort of confidence do you have that you have all of the variables represented that you possibly need? And if you did not collect it, and even if you did, how do you know it's not biased? How do you know that the collection method didn't somehow bias statistically the data that you're training off of? The next problem is one of confounding factors. This is a really interesting philosophical scenario that I stole, and it's one of intervening causes. So imagine you are trapped in the middle of a hot desert, and you have basically one barrel of water to keep yourself alive. Unfortunately, you have two bad guys, two enemies who are out to get you, both of whom are trying to kill you. The first of which is going to try to kill you by draining your supply of water. The second of which is going to try to kill you by poisoning your supply of water. Now, after the fact, let's say law enforcement, whoever that might be, catches up with these guys, interrogates them, gets them to confess. The second bad guy over there on the right is, fesses up and he says, yeah, okay, I tried to kill you. I put poison in your water. But upon hearing that, The first bad guy is like, well, you know what? I drained your supply because I was actually looking out for your best interest. I was trying to, you know, lengthen your life and not have you drink the poison. So here we have a case of obvious preemption of effect, whereas both of these guys were out to nefarious purposes. Both of them would have caused death of whoever was dependent on the water. One maybe a little bit faster than the other. But the counterfactual in this case is not going to necessarily reveal the right causal agent every time. Next up is the dreaded set of common causes. And the canonical example here is a fire. We're taught as young children that there are basically three things that you need to make a fire. You need oxygen, you need heat, and you need fuel. So if I use the counterfactual test and I remove oxygen from the equation and the fire goes out, I can say, aha, oxygen was the cause of the fire. Not so fast, right? Because if I had removed heat, the fire would have gone away too. And the same would happen for fuel. In fact, the same would happen if you removed all three simultaneously. So the problem is that the counterfactual tests aren't necessarily going to tell you if there are multiple causal agents. It's certainly not going to tell you how many multiple causal agents there might be. And you're left wondering, you're left with a black swan problem at this point, wondering if you have enough variables in your data set and if there aren't other potential causes in the mix that you may have missed. All right, so how do we get past all this, right? So the great Judea Pearl basically got us out of this situation with a term he calls sustenance. Imagine a new world in which we've introduced some structural contingencies. And in those contingency inflicted world or multiple worlds, we're gonna perform the counterfactual test. Now, what's better than one new world is 1,000 new worlds. Enter the Monte Carlo method. For those of you who are still as of yet unfamiliar with the Monte Carlo method, it gives you a middle ground that is not quite math, not quite science, but it enables you to run a simulation thousands and thousands and thousands of times under different probability distributions, under different initial conditions, under different parameters the entire time. And you can, with the advent of modern computers, you can do this thousands, if not millions of times in a row. And the diagram I have here is just a simple explanation of how it's used today to help predict the weather. This technique was developed historically for the Manhattan Project to solve the multi-body problem, which so perplexed the great minds of the day. Okay, so that's the first big advancement, is getting to real causality and all the problems and challenges that stand in our way to do that. So what's the next big advancement? The next big advancement is what I told you at the beginning. We're going to try to create autonomous systems that are improved by rules-based systems, which then improve the autonomous system again, which continue to improve the rule-based system, and so on and so on and so on in a nice, convenient feedback loop. And the link, as you'll see later, is going to be that causality link. Why are we going to do this? Because the path to the result is as important as the result itself, right? Imagine two people, both of whom are going to end up at the end of their life with $1 million in the bank. The first one ends up with $1 million in the bank because he walks into a casino, puts $100 down on a roulette wheel and gets lucky, and walks out of the casino with $1 million. The other one works hard as a dentist, a doctor, an engineer, scientist, and works hard and steadily accumulates $1 million over their career. The point here is that those two things, while they might end the same way, are very, very path dependent. And in the multiple worlds, multiple universes that I just described in a couple of slides ago, the person who got his $1 million by getting lucky at the casino would find it very, very difficult to have $1 million in any of the other scenarios that might have played out in those multiple worlds. Whereas the folks who consistently acquired their wealth through practice and supply and demand and good careers are more than likely to achieve the same result in all the or most of the multiple worlds. The point here is that good models closely reflect the real world. They get better with more data, they don't get worse, right? If you have a model and you feed it more data and it doesn't get better, you need a different model. And good models are consistent over long periods of time. They don't just get lucky once. They need to be run, they need to be tested. We had some previous speakers bring up the notion of continual testing, red team pen testing of AI models. And I think that fits in here nicely. Why do we do this? Because our most valuable models are very deterministic. Deterministic models are testable, they're understandable, they're able to be verified, they're easy to debug, and they're really clear when they're wrong or if something went wrong with the model. And we'll get to this in a second. The first one is the notion of testability. So the picture here is hearkening back about a decade to the Toyota unintended acceleration fiasco. And the real question is, how do you know if there's been a mistake? How do you know if there's been a fault in the model or a fault in the system? And the point is that even if you do millions and millions of miles of road testing on your cars, it's still not enough if you're putting millions of cars on the road and people are driving them for hundreds of thousands of miles over decades of time. In fact, when the NASA engineers came in to sort of rescue the evaluation of the unintended acceleration incidents, what they found was that the Toyota software was inherently untestable in the first place. The next big question is, can you actually tell when there's been a mistake? And actually, when I first put this image into PowerPoint, it was too ironic not to include the alt text that Microsoft PowerPoint wanted to suggest that this picture was. So the caption that it wanted to generate for this picture was a picture containing indoors. Even though it's clearly got a hand, it missed the hand, it missed the blocks, it missed the alphabet blocks, it missed the table. It was just completely off. So you need to have something more than just your AI, your non-deterministic probabilistic model to help tell you when the original model is actually making a mistake. The next question is, how can you ever validate your predictions? If you're building a predictive model and you can't get ground truth for what you're trying to predict, for example, we can have a bet as to who's going to win the next Super Bowl. And based on the fact that there will be a next Super Bowl, we can wait until February or whenever the next Super Bowl is. And at the end of the game, there will be a winner and we will be able to determine who is right and who is wrong. But the picture here is ghosting facial recognition a little bit. If there's no way to tell good from bad, and you're going to have a prediction or a classifier on something that might take decades, if not lifetimes, before it will be proven out, how are you even going to know that your prediction is valid? How are you going to train your data? The next big gotcha is that of undecidable problems. I've run into too many researchers and too many research efforts that have succumbed to the hubris of thinking that they've come across the best answer, the best solution to a problem, when in some cases there mathematically is not a best answer at all. And I've provided the example over here on the right of Conway's Game of Life. Mr. Conway, who unfortunately passed away from us this year, invented the Game of Life, which is still paying dividends to those of us in the mathematics and the science communities. If you're unfamiliar with the Game of Life, it starts with a bunch of blocks on this grid, and based on an initial pattern, we'll create new blocks and remove blocks from the original pattern based on how many neighboring units there happen to be, and thus evolves a pattern as it grows and evolves across the grid. The problem with this is that given an initial pattern and a later pattern, there is mathematically no algorithm that can exist to tell you whether you can get one pattern from the other. So here's a really easy example of a problem that's largely undecidable from the beginning. The last one is the dreaded rare event. I can hear folks in the audience already saying that, yeah, but my data science team, they've got a model and it's super accurate. The false positive rate is so close to zero. It's just really good. And the problem is that rare events happen all the time. In fact, the odds of winning the grand prize in Powerball are somewhere on the order of 1 in 300 million. However, in 2016, when the drawing reached $1.6 billion for the jackpot, that week saw 3 people share the jackpot in the same drawing. All right, so why don't we just use the deterministic model then? All right, well, we work in reality, and reality will always trump us. This example I draw from Norton. It's called affectionately Norton's dome. And it basically is a dome with a ball perched atop of it. It's a metastable system in which one of two things is going to happen. Either the ball is going to remain completely motionless, or it's going to fall and roll down the hill. The problem is it rolls down the hill at a random angle. It is a completely non-deterministic set. And the reason why you can see that, if you're interested in the fully detailed proof, I'll point you to the paper, which is over there on the right. But the quick description is that Newton's laws of physics are reversible in terms of time. So if you imagine the ball at rest at the bottom of the hill and flicking it with your finger with just the exquisite amount of force so that it remains perched motionless up on top of the hill, you'll see that you could have done that from any location along the bottom, and thus the ball could roll down the hill at any angle. So here we have something that obeys Newton's laws, yet is completely non-deterministic. The other reason we can't just rely completely on the deterministic system is sometimes those models aren't practical. Here we have a very nice, concise set. If you're into differential equations, it's concise for the Lorentz equations. Again, if you're not familiar with the Lorentz equations, these are the famous equations originally developed to help model and predict weather patterns across the globe, and were the beginning of chaos theory and the quote-unquote butterfly effect. Because what happens here is that even though it's a completely deterministic model and a deterministic system, even the tiniest change in initial conditions will result in wildly different paths later on. Sometimes the deterministic models are just too complex, right? There's not a lot on this slide because complexity is relative. What's complex for one organization is not for another. So I'm basically just going to say that sometimes for the deterministic models are just going to be too complex for the group. The deterministic models also may have too much uncertainty, and you can't model what you can't understand, right? If you're trying to model a process that's largely human behavior or Mother Nature, Mother Nature doesn't tell you how many slots there are on the roulette wheel, right? We might know that there's uncertainty in the problem, but we have a very hard time quantifying exactly how much uncertainty there is. Okay, so I was brought up to not just point out problems, but to anytime you point out a problem, you got a positive solution. So here are a few things that we have been working on at the Office of Naval Research that are really seem to be working out for us. So this is what we can do about it. The first thing we're going to try to do is we're going to try to put those deterministic systems in that feedback loop together with a non-deterministic system, i.e. an artificial intelligence machine learning model, because we know no matter how good the AI models are, the machine learning models, there's one guarantee, and there's a guarantee that they will make a mistake at some point. We know that there are problems with the training data. We know that there are adversarial examples, but moreover, we know that it's a non-deterministic, probabilistic black box that is guaranteed to run amok at some point. The question is, how much do those mistakes cost, right? We've seen a number of examples across the former speakers today, but if you look at the areas where AI and machine learning has been wildly successful, they have been things like image classification, handwriting recognition, things, speech to text, natural language translation. They're things where mistakes may not cost a lot of money, right? If you're an internet search provider and you miss an ad placement, you might miss a microtransaction, you might miss an ad buy. But if you're the Department of Defense, or you're the intelligence community, or you're an auto manufacturer or an avionics manufacturer, those mistakes might cost lives. So if we're in one of those situations, we would still like to take advantage of the artificial intelligence and the machine learning models, but how do we actually do that? And can we actually bound it with a deterministic model to help us out? This one, somebody already stole my thunder on this one. So here's the great Mr. Kahneman on the type 1 and type 2 thinking, right? So this is how humans do it. On the one hand, we have the really quick gut feeling, intuitive, associative, largely unconscious but error-prone style of thinking, right? And on the other hand, we have the meticulous, methodical, conscious, highly analytical, but also analysis paralysis, indecisive brain. So how can we actually do this with the models that we've been talking about? And before we tackle that, let's see how this notion plays out in real life. Let's say we have a test for something that affects, on average, 1 in every 1,000 people. The test produces only 1 false positive in 1,000 and no false negatives. So what's the chance that somebody who tests positive has that something? Well, the gut feeling brain says, wow, you had only 1 false positive in every 1,000. That's a pretty accurate test. I'm going to say pretty high. But the reasoning side of your brain says, wait a second. If I test a cohort of 1,000 people, there's going to be 2 positive results. There's going to be 1 that was the false positive, and there's going to be 1 that's the true positive. So that's a 50-50 chance, and you're no better than a coin flip. So this is the base rate fallacy, or the false positive paradox. And this has tripped up the human brain forever, right? People still fall for this all the time. And in fact, a variation of this question was given to doctors, and it was rather amazing how many doctors actually got this question wrong. So here's what we're doing on the advanced research side. Here's how we're trying to get those 2 models stuck together. The observation is that if we have an AI model and we have a formal reasoning model, the AI model tends to be very, very good at inferring and sensing and collecting the perception data. It samples the world very well, and its quality depends on the amount of training and the number of training samples. But because of its probabilistic representation, it can deal with the uncertainty pretty well. The problem is you get a combinatorial explosion at the planning level, right? Contrast this with the formal models, which are slower, more rigorous, more logical, where the quality depends on the logical structure and the logical rigor. They tend to be a little more difficult to get to complete because of that logical structure. They tend to also be rigid because of that logical structure. But they're very analyzable, they're very abstractable, and they tend to give you the planning aspect better, where you get the combinatorial explosion at the sensing level. Now, wouldn't it make sense if we could actually combine these and get the best of both worlds and have our cake and eat it too? So that's what we're going to try to do. We're going to try to put these 2 things together, and we can do it 2 different ways. We can do it in serial, and we can do it in parallel. So if we do it in serial, this so-called stacked model, where we have data acquisition at the bottom, number of observations feeding into the AI and the machine learning model, and then that AI machine learning model will interact with a formal reasoning model to take over and essentially provide the guardrails. It will give you that out-of-band model to help you understand where the probabilistic, non-deterministic model may have been wrong, and kind of bring you back on track and get you to the decision of the plan. The other way we can do this is we can do it in parallel, where we can again start with data acquisition, feeding the statistical learning model first, and then after some period of time, we can have the formal reasoning model, the formal model, learn from the AI and the machine learning model and pass back new information based on the reason from the model on the left. And we can put them in a feedback loop sort of continuously. This is a little more difficult because there's a number of interactions between the systems, but we're essentially going to do the same thing, just in parallel instead of in serial. So how does this all come full circle? What does this actually look like in real life? And how do we actually put some formalism behind that interaction layer that I was just kind of waving my hands at a minute ago. Well, the glue between those models, that interaction layer, is exactly what we talked about before, which is the ability to infer causal agents in the system. So what you get is you can have the learning model on the left, the reasoning model on the right, and out of every iteration, you will get newly discovered facts, and you can validate some heuristics that you might learn from the learning model, and you can now apply those and make the reasoning model better. Likewise, you can get new training samples and new logical bounds from the reasoning model and start to apply those into the AI model, and then rinse and repeat over and over and over again. Essentially, the AI and the learning model can deal with the uncertainty and produce the dots from the sensing and from the data, and the reasoning model can help you connect those dots, propagate the predictions, and each model strengthens the other one. And the only way to get there is gluing them together with what's common in both of them, which is the causal inference. So it comes full circle all the way back to Mr. Hume, where basically, reason is and ought to be the slave of the passions. Back in the mid-1700s, already sort of predicting the fact that we would need to put these two styles of model together. The questions for the group is, so what does this mean for you? So I work within the research space of the Office of Naval Research. So they're largely Navy problems. I am not an intelligence community expert. And the space where we have seen this technique to greatest effect has largely been in cybersecurity. So I've actually posed a couple questions back to the group here. What we know is that integrating AI and machine learning models together with the rules-based models allows both of them to be more resilient than they ever were on their own. And the hybridized approach allows us to essentially tolerate the risk of mistake making that is inherent in the AI and the machine learning to tolerable levels, so that we can actually use it in cases where we might not be able to use it or tolerate it otherwise. So the question to the group is, what problems is this community seeing? And I really look forward to the panel and the open Q&A on this one. What kind of problems do you see, if you believe me, that we can actually stick these models together and have our cake and eat it too? I put a few on here. There's optimizing the PED process. There's explainable decision making. I stopped short of explainable AI, but and then there's also a big use case in terms of maximizing the use of commercial technology, where we want to take advantage of what the commercial industry is able to bring, but we may not necessarily trust every little bit of it, or we may want to tweak it so that it is useful for our purposes and a little bit different than what we might get right out of the box from the commercial vendors. With that, I'll thank the group again. And I think we have a few minutes. So Joe, I'll pass it back to you, and I'll let you determine whether or not we want to just break until the panel or whether we want to take some questions now.
On mute. Well, we do have a rather long break before the panel. Could you entertain a couple questions?
Absolutely.
Okay, why don't we field a few questions from Matt now, and then we'll break for the panel later.
So let me just let me look through some of these. I see some common themes here with how do you integrate things like Bayesian models? What's the proper role of Bayesian models? Bayesian models actually help you do some of that connective tissue in the causal relationships, because they can help you essentially anytime you're updating your prior and updating your belief, you can use that to essentially update either heuristics that you're going to apply in the deterministic model, or give you some new guardrails and improve the learning in the AI model. Let me, as I'm looking through here, let me know if you see any other prominent trends.
Sure.
Or is AI approach necessary for physical sciences, not necessarily engineering? I think the AI-based approach, especially when blended like this with a deterministic model that it can be paired up with, is fantastic for the physical sciences, especially if you expand beyond just the traditional physics of physics sciences, but when you get into chemistry. The pharmaceutical industry, for example, has been using AI and machine learning, predictive models generated by those to essentially identify the shapes of new drug compounds that tend to be similar with other ones. And the reason why that's been largely successful is they don't just blindly trust the AI and the machine model. They use it to essentially give them hints about what they should be looking at. And then they pair it up with the deterministic laboratory testing to essentially validate. So absolutely yes in the physical sciences. Let's see, AI workflows for the layman. This is a fantastic question because this one, AI workflows for the layman is a double-edged sword, right? We want to be able to have as many practitioners be able to use AI and machine learning as possible. The gotcha though is the understanding of what's inside that black box. You really, really, really need to understand the math and the probability that's inherent in a lot of the AI and machine learning algorithms that's under the hood, or else you really don't understand the answers that are going to come out of said models. So that one is very, very tricky. Let's see. Can we get copies of the slides? That's an easy one. Yes. Let's see. AI as an option to teach mathematics, interactive avatars used in employee training and other learning contexts. This is another great example of where AI really shines in a low cost of failure. So if there's a failure within an avatar, it might look funny. It might have a hitch in the speech or something like that. But unless the hitch actually rises to replacing the wrong word with a catastrophic word, usually the failure in an avatar is not going to be terribly costly. So AI for training and learning contexts, I think is, at least from what I've seen, is pretty good. Let me see, any other questions as I've been going through here? How should Navy compare AI machine learning model types? That's a really good it depends question. It really depends on the AI and the machine learning that you're using. In the world that I live in, which is largely cybersecurity right now, it even still depends. So we're seeing AI machine learning models that are particularly adept at classifying different pieces of code. I tend to shy away from any good versus bad detector, hearkening back to the puppy dog slide. But we've seen really good results with trying to apply language translation to computer science, right? Essentially treating executable code as a language and doing a translation of what would otherwise be called machine code or assembly code back into pseudocode or pseudo source code using some of the language translation models. So there's some really interesting work in reverse engineering and feature identification there. That also extends to communications protocols as well. There's some really interesting stuff happening with comms protocols. So depending, AI and machine learning models, I think, should largely be judged on the domain in which they are applied and use the domain-specific language and the domain-specific metrics that are most important for the domain. And so I think one other prediction that I would have as to the future of data science is that I think you're going to start to see a lot more, not fragmentation, but I think you'll see a lot more specialization. Whereas we might call it data science today, I think there will be a very specific field of data science for medicine, which will look very different from a data science for cyber, which will look very different for data science for intelligence community. And I think we'll start to see a lot more lines develop in what kinds of tools and what kind of techniques work best in the individual domains. All right, I think I got everything.
Matt, maybe you can answer one question that I've had for a long time, which is, is there a new mathematics that will emerge AI? That is to say, my own view is, or my own education says that most mathematics tools used in it really have been around for a long time. Large systems of simultaneous linear equations, etc. And the only reason it works so well is because we have good computers and good algorithms to process the data. So my question is there behind is there new mathematics that we should be expecting out of this field?
I'm not going to deign to predict the rise of an entirely new science within mathematics, but what I can say is I have not really seen one emerge yet. What I have seen from my perspective at the Office of Naval Research is largely old mathematical constructs applied in new ways, right? Inside the AI and the machine learning box, there's a lot of optimization that goes on. There's a lot of differential equation. And we're seeing new elements of that field. Whether or not that will develop into its own field that is specific for machine learning or not, I can't say. But as a purist, I would probably say no. I would expect that to fall under optimization theory and the computer science of machine learning at this point.
Okay,
but
great.
I will not deign to say.
Yeah, I know it's difficult. It's an unanswerable question right now. It's time to take a short break before our panel session. Matt, welcome back for that, and we'll entertain a broader scope of questions at the panel session, which will reconvene in about 10 minutes or so. See you then.